Hello and welcome to this week's episode of the Galaxy Report. The Galaxy Report is here as a part of thedailygalaxy.com. I'm Nicole Butcher, and today we're going to be talking about the findings of two of NASA's probes, Juno at Jupiter and Cassini at Saturn. Both probes have been able to make remarkable discoveries and observation. However, some things still remain a mystery. Like what caused Saturn's Cassini spacecraft to experience weird pulls? Well, we're going to be discussing some potentials in this episode, as well as much more. While I was making the music for today's episode, I really wanted to keep Saturn and Jupiter in mind. So I hope you're somewhere comfortable and enjoy a nice, relaxing episode. Radio signals from two NASA space probes have allowed researchers to pierce the swirling clouds that hide the deep interiors of Jupiter and Saturn together, where crushing pressure transforms matter into states unknown to Earth. The two planets are more complex than we thought, says Ravid Halid, a planetary scientist at the University of Zurich in Switzerland. Giant planets are not simple balls of hydrogen and helium. It's a shame we don't have it naturally on Earth. But on Jupiter, there are oceans of metallic hydrogen. We want to find out how these oceans give rise to Jupiter's enormous magnetic field, observes Mohammed Zaghou with University of Rochester's Laboratory of Laser Energetics, and colleague Gilbert Collins, director of the High Energy Density Physics program. Astrophysicists have long thought that terrestrial planets with magnetic fields are better able to sustain gaseous atmospheres, and more likely to harbor life. One of the biggest mysteries surrounding Jupiter is how it generates its powerful magnetic field, the strongest in the solar system. One theory is that about halfway to Jupiter's core, the pressures and temperatures have become so intense that the hydrogen that makes up 90% of the planet loses hold of its electrons and begins behaving like a liquid metal. Oceans of liquid metallic hydrogen surrounding Jupiter's core would explain its powerful magnetic field. Dynamo theory and magnetic fields are key conditions of habitability, says Zaghou. There are hundreds of exoplanets discovered outside our solar system each year, and we think many of these planets are like Jupiter and Saturn. We can't go to these planets yet, but we can apply our knowledge about the supergiants in our own solar system to make models of what these planets might be like. Metallic hydrogen is one of the rarest materials on Earth. Yet, more than 80% of planets, including Jupiter and Saturn, are composed of this exotic form of matter. Metallic hydrogen is the most abundant form of matter in our planetary system, says Zaghou. Despite its rarity on Earth, making metallic hydrogen an intriguing focus for researchers who study planet formation and evolution, including how planets both inside and outside our solar system form magnetic shields. By studying the conductivity of metallic hydrogen, Zaghou and Collins are able to build a more accurate model of the dynamo effect, a process where the kinetic energy of conducting moving fluids converts to a magnetic energy. Gas giants like Jupiter have a very powerful dynamo, but the mechanism is also present deep within Earth, in the outer core. This dynamo creates our own magnetic field, making our planet habitable by shielding us from harmful solar particles. Researchers can map the Earth's magnetic field, but because the Earth has a magnetic crust, satellites cannot see far enough into our own planet to observe this dynamo in action. Jupiter, on the other hand, does not have a crust barrier. This makes it relatively easier for satellites like NASA's Juno space probe to observe the planet's deep structures, says Collins. This effort, writes Paul Vucin in Science, led by Luciano Les of Sapienza University in Rome, turned the radio signals into probes of gravitational variations that originate deep inside these gas giants. The results have been published in Nature for Jupiter and in Science for Saturn. In the 1980s, Les helped pioneer a radio instrument for Cassini that delivered an exceptionally clear signal because it worked in the Ka band, which is relatively free of noise from interplanetary plasma. By monitoring fluctuations in the radio signal, the team planned to search for gravitational waves from the cosmos and test general relativity during the spacecraft's journey to Saturn, which began in 1997, as well as from a similar device on the Juno mission to Jupiter, which launched in 2011. Les and colleagues used radio fluctuations to map the shape of gravity fields at both planets, allowing them to infer the density and movements of material deep inside. One goal, reports Science, was to probe the roots of the powerful winds that whip clouds on the gas giants into distinct horizontal bands. Scientists assumed the winds would either be shallow, like the winds on Earth, or very deep, penetrating tens of thousands of kilometers into the planets, where extreme pressure is expected to rip the electrons from hydrogen, turning it into a metal-like conductor. The study's results for Jupiter were a puzzle. 500 kilometer per hour winds aren't shallow, but they reach just 3,000 kilometers into the planet, some 4% of its radius. Saturn then presented a different mystery. Despite its smaller volume, its surface winds, which top at about 1,800 kilometers per hour, go 3 times deeper than Jupiter's, to at least 9,000 kilometers. Everybody was caught by a surprise, Les says. The Juno and Cassini data yield only faint clues about greater depths. Scientists once believed the gas giants formed much like Earth, building up a rocky core before vacuuming gas from the protoplanetary disk. Such a stately process would have likely led to distinct layers, including a discrete core enriched in heavier elements. But Juno's measurements, interpreted through models, suggests Jupiter's core has only a fuzzy boundary, its heavy elements tapering off for up to half its radius. This suggests that rather than forming a rocky core and then adding gas, Jupiter might have taken shape from vaporized rock and gas right from the start, says Nadine Nettleman, a planetary scientist at the University of Rostock in Germany. And yet, the picture is still murkier for Saturn. Cassini's data hints that its core could have had a mass of some 15 to 18 times that of Earth, with a higher concentration of heavy elements, more so than Jupiter. This suggests a clearer boundary. This interpretation is tentative, however, says David Stevenson, a planetary scientist at the California Institute of Technology and co-investigator on Juno. What's more, Cassini was tugged by something deep within Saturn that could not be explained by wind, Les says. We call it the dark side of Saturn's gravity. The most likely explanation for this accidental gravity is normal modes, oscillations of Saturn, essentially long wavelength sound waves, but not unlike those we see on the Sun or Earth, Stevenson wrote in an email to the Daily Galaxy. Whatever's causing this tug, Stevenson adds, it's not found on Jupiter. It is a major result I don't think we understand yet. We don't know yet what exactly causes this, but I suspect these longitudinal variations in the gravity field are due to deep storms or internal convection, geophysicist Yohai Caspi at the Weizmann Institute of Science wrote in an email to the Daily Galaxy. These variations are somewhat similar to the variations that were recently detected on Jupiter due to the Great Red Spot. There's not going to be a better measurement anytime soon, says Chris Mankiewicz, a planetary scientist at the University of California, Santa Cruz, of the Cassini mission, which is ended with a grand finale, culminating with the probe's fiery and deliberate destruction in Saturn's atmosphere. A well-thought-out experiment to get data by crashing the satellite into the planet. Although the rings complicate the gravity measurement, they also offer an opportunity. For some unknown reason, perhaps it's the winds or the pull of its many moons, Saturn vibrates. The gravitational influence of these oscillations minutely warps the shape of its ring into a pattern like the spiraling arms of a galaxy. The result is a visible record of the vibrations, like the trace on a seismograph, which scientists can decipher to plumb the planet. Mankiewicz says it's clear that some of these vibrations reach deep into the interior, and has already used ring seismology to estimate how fast Saturn's interior rotates. Cassini's last gift was data from the spacecraft's final orbit that enabled Les's team to show the rings are low in mass, which means they must be young, as little as 10 million years old, reports Vucin. Encroaching interplanetary soot would have darkened the gas giant's brilliant rings. They continue to rain material onto Saturn, the Cassini team has found, which could one day lead to Saturn's demise. We see so much more, and closer up, and we're getting new and more interesting puzzles, said NASA's Ames Research Center Jeff Cousy, who's been studying Saturn since the 1970s, and is the interdisciplinary scientist for rings on the Cassini mission. We are just settling into the next phase, which is building new, detailed models of ring evolution, including the new revelation from Cassini data that the rings are much younger. Findings include fine details of features sculpted by masses embedded within the rings. Textures and patterns, from clumpy to straw-like, pop out of the images, raising questions about the interactions that shaped them. New maps reveal how colors, chemistry, and temperatures change across the rings. Like a planet under construction inside a disk of protoplanetary material, tiny moons embedded in Saturn's ring interact with the particles around them. In that way, the paper further provides evidence that the rings are a window into the astrophysical disk process that shape our solar system. These new details of how the moons are sculpting the rings in various ways provide a window into the solar system formation, where you also have disks evolving under the influence of masses embedded within them, said lead author and Cassini scientist Matt Tisakerno at SETI Institute. Cassini and Jupiter are bringing scientists closer, not just to understanding Jupiter and Saturn, but also the formation of our own solar system. Even though it is still a mystery as to what was pulling on Cassini. For me, it brings up the paradigm of the more we seem to know, the more we seem to not know. Or the more we find out how much we don't know. These stories were published first on thedailygalaxy.com with the help of Avi Shapur, who's a research scientist at the MIT Cavalli Institute, and Daily Galaxy's editorial team. I'm Nicole Butcher, and I hope you enjoyed today's episode. Make sure to like and subscribe, and I'll see you guys next week.